the lecture on instruction scheduling. So, in this lecture we will be looking at machine dependent optimization, and instruction scheduling is one of them. We have seen one type of machine dependent optimization before, that is the peephole optimization. That was a very simple optimization looking at a window of instructions to find patterns and then replace that pattern with a more efficient sequence of instructions and so on. Instruction scheduling is different. So, there are many types of instruction scheduling mechanisms. We are going to see a few of them. Basically, all instruction scheduling mechanisms consider a sequence of instructions in one or more basic blocks. The minimum of course is one basic block. Then based on different criteria, they try to reorder the instructions. Why should these instructions be reordered? Well, basically we want to make sure that the pipelines in the processor, they remain full most of the time, and any hiccups in this pipeline are avoided. So, we see how best it can be done by using instruction reordering. So, simple basic block scheduling, then automaton based scheduling, integer programming based scheduling, optimal delayed load scheduling for trees, and then trace, super block and hyper block scheduling are some of the instruction scheduling mechanisms, algorithms that we are going to consider. So, what exactly is instruction scheduling? As I mentioned, it is nothing but reordering of instructions, so as to keep the pipelines of the functional units of a processor with no stalls. So, no hiccups, and instruction scheduling in general is an NP complete problem, and therefore, there is a need for heuristics to take care of instruction scheduling. If it is applied on basic blocks, then it is called local instruction scheduling, and if it is applied on a sequence of basic blocks, then it is called global instruction scheduling. So, global scheduling requires elongation of basic blocks. So, and these are called super blocks, hyper blocks, etc., etc. So, let us look at some motivation, why exactly instruction scheduling is needed, what are its advantages and so on. Consider this sequence of instructions here. So, we have 7 instructions, and we are considering a load store architecture. In other words, any operand must be in a register. So, we have to load the operand into a register and then use it. That is the model that we are considering here. So, time to load is 2 cycles, and each operation requires 1 cycle. In this code, this is the dependency graph, directed acyclic graph for this particular code. If you observe this code with the latency that is given here, 2 cycles for load and 1 cycle for op, we immediately see that there are 2 stalls, one at I 3 and another at I 5. Let us see why. So, I 3 loads R 1 plus R 2, computes R 1 plus R 2 and puts it into R 3, and R 1 and R 2 are loaded into loaded from A and B in the instructions I 1 and I 2. The instruction I 1 would have completed by the time we reach I 3, because 2 cycles would have been completed, but the instruction I 2 which loads B into R 2 would not have completed when we come to I 3. So, there is a need to skip one cycle here, and that is the stall that we are talking about. And once the result of load instruction in I 2 is ready, the computation of R 1 plus R 2 can take place. Similarly, the instruction I 5, it has R 5 equal to R 3 minus R 4. R 4 is being loaded from a memory location C in the instruction I4, it is not yet complete, and therefore, there is a stall at this point. We have to skip an instruction and then execute the instruction I5. So, that means instead of these 7 instructions will really require 9 cycles in order to complete. So, now suppose we want to get rid of these stalls. Is it possible to reorder these instructions such that the dependencies as given in the directed acyclic graph are still satisfied? In other words, we definitely want to wait for the loads to be completed before we come to I3, that is the operands must be ready before we come to I3. Similarly, we want to make sure that R4 is ready before we come to I5. Only thing is some reordering of instructions may be possible. So, let us see how. So, here is a new sequence of instructions. There are no stalls here, but dependencies are indeed satisfied. How are the stalls eliminated? I1 remains as it is, I2 remains as it is, but I4 is actually replacing the instruction I3, and I3 has been pushed down by one cycle. So, in the one step. So, now when we arrive at the instruction I3, which is R1 plus R2, both R1 and R2 are ready. The reason is R1 takes 2 cycles. So, it will be ready by the time I4 is executed. R2 takes 2 cycles. So, that will also be ready by the time I3 is executed. So, R1 and R2 will now contain operands, there is no stall. R4 of course, would not have completed by the time we execute I3, but it is not required in the instruction I3. So, once we finish I3, we execute I5, which requires R4, and R4 would have got its operand by the time we reach I5, because 2 cycles have lapsed. So, this particular sequence of instructions actually completes just 7 cycles, it does not take 9 cycles at all. That is because we have just swapped this instructions I4 and I3, all others have remained the same. So, I4 is in the slot with the load instruction and I3 is in this slot with the computation instruction. So, this is a very simple example which shows that a subtle change in the order of execution of the instructions will lead to removal of the stalls. That does not mean every stall can be removed. There will be some stalls which cannot be removed, as we will see in later examples. We will have to insert no ops in those stalls, in those cycles. So, quickly to recapitulate what we need here, we definitely want to look at the same dependencies flow, anti and output as we studied in parallelization, but these are now at the register and load levels. Okay. They are not at the higher levels, but between statements etcetera, they are at the machine instruction level. For example, I1 is R1 is loaded with load of R2. So, and then I2 is R3 equal to R1 plus 4 and I2 is R3 equal to R1 plus 4 and I3 is R1 equal to R4 plus R5. So, here the value which is actually loaded into R1 is used in I2. So, I1 delta I2 holds. Similarly, whatever is loaded into R3 okay, is actually it is sorry, whatever is read from R1 is later replaced in instruction I3. So, there is an anti dependence between I2 and I3. So, that is I2 delta bar I3, and then we also have I1 delta naught I3, because we are actually loading into the same register R1. I1 and I3 are related by output dependence. So, anti and output dependencies can be eliminated by register renaming. We have seen some examples of this in parallelization. So, for example, here we do not use R1, we just use say maybe R6 or something like that, then automatically there is no output dependence between these two. So, and that automatically eliminates this anti dependence as well. So, what is a dependence directed acyclic graph? Well, it is the same dependence graph as we studied in parallelization. It is just that here we have at the machine instruction level. So, here is a simple example. This is the sequence of instructions, which is a running example that we are going to use. So, I1 to I9, 9 instructions. There are 9 instructions here, 9 nodes here. These are the nodes of the directed acyclic graph. Each instruction is a node. There is a solid arc from one node to another node, and that shows a flow dependence. For example, between I1 and I3. Okay. So, T1 is equal to load A, T3 equal to T1 plus 4. So, there is a load, there is a flow dependence. Similarly, another flow dependence between I1 and I4, and so on and so forth. So, all the flow dependences are shown in solid lines. Then the anti dependences are shown using the dashed line. So, this is the dashed line from I1 to I9. So, here is I1 and here is I9. So, you may wonder why load A in I1 and B equal to store T5 in I9 have been linked by an anti dependence. The reason is memory disambiguation, which says that this A and this B are different, has not been done. So, no algorithm has been applied to find out whether A and B are the same location or are different locations. So, because of that, conservatively we will have to assume that there is an anti dependence from I1 to I9, because A and B could be the same. Similarly, B this B of course is the same. So, I2 and I9 also have a dependence. So, this is I2 and this is I9. Okay. So, here I2 and I9. Similarly, I1 and I8, I2 and I8 also have similar anti dependence. So, here and here. Okay. So, these are the anti dependences that need to be depicted in this dependence diagram. Then there may be output dependences. So, those are shown by dash dot line. So, here is an output dependence, and output dependence is between these two. Again, memory disambiguation has not been done. So, we do not know that B and C are different memory locations. So, there is an anti dependence from I8 to I9, sorry, there is an output dependence from I8 to I9. So, the dependence diagram shows all this. Now, the problem of instruction scheduling would be to rearrange instructions in this sequence, so as to respect all these flow, anti and output dependences, yet minimize the number of stalls that may occur in the sequence. So, the first algorithm that we are going to study is the basic block scheduling. So, what is our model? We need to study the model of a basic block. So, a basic block is assumed to consist of what are known as micro operation sequences, MOS, which are indivisible. In other words, if an instruction contains 3 or 4 micro operations in it, we need to, once we start that instruction, all the micro operations in it will have to be completed, and there is no way we can divide this sequence of 4 micro operations into 2 each and schedule them separately. So, once the instruction is started, all the micro operations will run one after another, they are indivisible. Each MOS has several steps, and each one of these steps will require resources. Each step of an MOS requires one cycle for execution. So, this is the assumption. There are precedence constraints and there are also resource constraints. These must be satisfied by the reordered or scheduled program. So, we have the diagram I showed here. This shows the precedence constraints. See. So, once we say there is a delay between these two, the delay on this edge could be the time of execution of the load instruction. Automatically, this becomes a weighted directed acyclic graph. and that shows all the precedences that must be satisfied. The precedences relate to data dependencies and execution delays, as I mentioned just now, but the dependence diagram does not show the resource constraints. So, resource constraints relate to limited availability of shared resources. So, in other words, suppose I want to execute this add, this sub and this add, and there is only one adder. It is, even though we may find that these three can be executed at the same step, it is not possible for us to schedule them in the same step, because there is only one adder. Compulsorily, we may have to schedule them in 3 successive cycles. So, that is what resource constraint is all about. Here is the basic block scheduling problem. So, first of all, the basic block is modeled as a digraph G with a set of nodes V and a set of edges E, and R is the number of resources that we are going to have in the system, in the processor. The nodes of the graph G are micro operation sequences, and edges of the graph E show the precedences. There is also a label on the node V instead of the edge alone, we also have a label on the node. So, the label on the node indicates a resource usage function. So, what is this? There is a resource usage function rho v I for each step of the MOS associated with I with the node V. So, in other words, if there are 4 steps in an MOS associated with node V, each of these 4 steps will require resources. So, rho v of 1 says how many resources of a particular type are needed for this particular micro operation sequence step. So, rho v 2 similarly for the second MOS step, and so on and so forth. So, these things actually we are considering only a single type of resource. R is the total number of resources. So, it is a simplified problem as such. If we have many resources, many types of resources, it is definitely possible to extend this problem to take care of those as well. It is just a question of checking all the resource constraints at a particular point in time. So, instead of just one vector of resources, rather one number indicating the number of resources, we would have a vector of these numbers saying how many are there in each particular type. So, the length L V of a node V shows how many substeps are included in the micro operation sequence at node V, and the label on edge E, any particular edge E, shows the execution delay of the MOS, and it is denoted by D of E. So, we have the resource requirements of a particular node V, E indicated by rho v of I for each substep I of that node, and we have on the label on the edges coming out of the node V or incoming edges of node V the execution delay of the particular MOS. So, now, the formal notation and description of the problem is here. The problem is to find the shortest schedule sigma, and sigma is a mapping from V to n. Why? For each node V, we need to find a time slot. The time slot is nothing but a natural number. So, which is the time slot in which V can be executed? That is the schedule that we want to find. For each node V, we want to find a particular number of that kind. And there are now restrictions. So, what are the restrictions? For all the edges E, say u comma v, in the set of edges E, sigma v minus sigma u must be greater than or equal to d of E. So, what does this tell us? Let us look at the picture. So, here is a node u, here is a node v, u has been scheduled at the time slot sigma u. Let us say node v has been scheduled at the time slot sigma v. Obviously, sigma v comes later than sigma u, because u must be executed before v. There is a precedence constraint rather edge connecting u and v, which says u must be completed before v. The delay on the edge u v is d. So, this delay d must be less than or equal to the schedule of v, which is sigma v, minus the schedule of u, that is sigma u. This is quite easy to understand, because we cannot start v before we complete sigma u. So, how much time does sigma u, rather completing u, how much time does u take? It starts at the slot sigma u, then it requires at least d slots more in order to complete. So, sigma u plus d is the minimum time at which we can start, that is why d less than or equal to sigma v minus sigma u. So, that is the precedence constraint, and sigma v minus sigma u greater than or equal to the delay on the edge E. What about resources? This says if you sum up all the resource requirements at a particular point in time, all the resource requirements must be less than or equal to R. So, let us understand this better. So, let us say we have this matrix, each row indicates an MOS corresponding to a node, say V 1, V 2, V 3, V 4, etcetera, etcetera. So, each one of these is a MOS, and since we know that one time slot is required for each one of these MOS substeps. So, here is the time slot of the MOS substeps. Okay. So, we are going to, this is not a valid schedule, it violates certain conditions, but this will tell you what the resource constraint is all about. Let us say the first MOS V 1 has been scheduled at time 0, second MOS at time 4. So, 1, 2, 3, 4, 4 steps are needed, 4 time slots are needed for sigma V 1 to complete, V 1 to complete. So, sigma V 3 cannot be started before the 4th time slot. Then we require 5 time slots for V 2. So, V 3 starts at 9, then we need 3 for V 3. So, V 4 starts at 12. We have taken care of all the precedence constraints, the delays and so on, but then this did not check the resource requirements. So, let us consider the red diagonal and the blue diagonal. Okay. So, first look at the blue diagonal. So, let us say we are looking at V 4 okay, in its second time step, rather sub step. Okay. So, at this point the elements in the matrix really show how many resource elements are needed for that particular sub step. So, for example, V 1 in time slot 0 requires 1 resource, in time slot 1 requires 1 resource, time slot 2 requires 2 resources, etcetera, etcetera. So, similarly, V 4 requires 1, 2, 3 and 2 resources in the time slot 0, 1, 2 and 3 are starting at 12. So, at this point in time, that is we are looking at, this is time slot 12, time slot 13, 14 and 15. Time slot 12 we require 2 resources because of V 4, but remember V 3 has not yet completed. V 3 started at 9. So, it is actually at it requires 9, 10, 11, right. So, all, so these are all the time slots that are needed for this particular node to complete. So, what we really say is, okay, let us see what are the various timing requirements and resource requirements of these slots. So, for example, this requires 2 here, 2 here and 2 here, these are all the concurrently executing threads that we have. So, the sum of all these is 5, right. So, when we have assuming that there are 5 resources in this particular system. So, the number of resources that we are using at a particular time, let us say is 5. So, we have 5 resources and utilization is also 5. So, the resource constraints are satisfied. but when you look at the red resources, okay, red circles here, we find that there is a violation. If you add up these 3 and 3 and 2, we really make it 8, right. So, because there are 8 resources being used, but there are only 5, at least we want to use 8, but there are only 5. That means, the number of resources available is less than the number of resources that we are trying to use. So, there is a violation. So, that is precisely what I said, this is not a valid schedule. If this were to be a valid schedule, this would not have occurred. We would have actually summed up these things to be less than or equal to 5. So, this is not a valid schedule, because the resource requirements at a particular point in time are actually beyond what is available in the system. So, that is what this is, rho v of I minus sigma v is less than or equal to r, that is what it should be, but it is not. And the length of the schedule in a valid schedule would be maximum of sigma v plus L v, where v is in v. So, we just take the maximum sigma v and L v, that is, if that is not the maximum of whole thing, one of the previous steps may have a smaller sigma v, but a larger L v. So, that may contribute to the maximum of the schedule. So, that is the meaning of this, right. So, we have demonstrated that at some point in time there may be satisfied resource requirements, but at some other point in time in an invalid schedule there will be violation of resource requirements. So, this should never happen, resource requirements must be satisfied at every point in time. So, how do we schedule the instructions so that the resource constraints and the precedence constraints are both satisfied? They find the shortest, here is a simple algorithm, and this is a variation of the very well known list scheduling algorithm that people have studied in operating systems, in job shop scheduling and so on. The requirement is find the shortest schedule sigma, which is a mapping from V to N, such that precedence and resource constraints are satisfied. And whenever there are holes, we assume that they are filled with no ops. So, here is a basic outline of the function called list schedule, which takes the DAG as its input v comma e. How does it work? It really does a topological sort of the graph. So, it starts with those nodes in the graph which do not have any predecessors. Those are the root nodes of V. Okay. So, the DAG may not be a single component, it may be a forest of DAGs, right. It is not necessary to have just one. So, in such a case the number of root nodes of that graph will be more than 1. There is a queue called a ready queue, which stores all the nodes which are eligible to be scheduled. Okay. So, root nodes of V are eligible to be scheduled because they have no predecessors, and when we begin with the root nodes of V, all the resources are assumed to be available. It does not mean that every node in the ready queue can be scheduled in the same time slot. We still have not found time slots for all the nodes in the ready queue. Okay. So, we just come from the top and include nodes as we go along. The schedule to begin with is phi, it has nothing. So, there is a loop while ready not equal to phi do. So, in which we actually take out nodes from the ready queue and then schedule it, put something else into the ready queue and keep doing this until all the nodes in the graph are scheduled. So, in that case ready list cannot get any more nodes. So, we stop when ready becomes phi. So, pick a node of highest priority from the ready queue and call that as V. So, how to do this? We will see a little later. So, let us assume that there is a prioritization of nodes in the ready list, and one of the highest priority nodes, the highest priority node is picked. Then we need to compute the lower bound on the time slots at which the node V can be scheduled. So, this is done by the function satisfy precedence constraints, which we are going to see very soon, V comma schedule comma sigma. Then once we have found the minimum time slot in which V can be scheduled, this is done by looking at the precedence requirements. We need to check whether that minimum time slot satisfies resource constraints, whether all the resources which are needed are available to us, and if so, fine, otherwise we need to actually keep that slot vacant, take the next slot, check whether resources are available at that point, and so on and so forth. So, this is done by the routine satisfy resource constraints V comma schedule comma sigma comma L B. So, once we have found sigma V, which is the time slot which satisfies both the precedence and resource constraints, we include that node as a scheduled node. So, schedule equal to schedule plus V. Then the ready list needs to be updated. So, what do we mean by updating? We take out the node V from the ready list. Here remember, we did not take it out. We take it out, then we try to add those successors of the node V, which actually are now ready to be scheduled. In other words, their own successors, for example, V is the node to be scheduled, which has been just now scheduled. There are 3 successors U1, U2 and U3 for this particular node. Then W1 and W2 are 2 other predecessors of U1 and U3, they have already been scheduled. So, U1 was waiting for V to be scheduled. So, now V also has been scheduled. So, U1 is now ready for scheduling. U2 has only V as its predecessor. So, U2 is also ready for its scheduling. U3 is similarly ready because W2 is already scheduled. So, V is now just now scheduled. So, this is also ready for scheduling, but another successor of V, which is X2, has a predecessor X1 which is not yet scheduled. So, even though V has been scheduled, X2 cannot be scheduled because X1 has not yet been scheduled. It can be scheduled only after X1 is scheduled. So, that is what we do here. We take out V and then include all those nodes U such that U is not in scheduled list. So, obviously, U should not have been scheduled already, and then for all W comma U in E, W must be already scheduled. So, for this node all its predecessors must be scheduled. W is the predecessor of U and U is now being put into the ready list. So, all its predecessors must already be scheduled. That is what we said here. X1 cannot be, is not yet scheduled. So, X2 cannot be included in the ready list, but U1, U2 and U3 will be included in the ready list. Now, what are the 2 functions satisfy precedence constraint and satisfy resource constraint do? They consider sigma U plus d of u v over all the scheduled nodes U. Okay. So, and then return the maximum of this value. So, let us see what it really means. So, we are looking at V, okay, and now we are looking at all the predecessors of V. So, that is what this said. See, sigma V is our node. We are looking at U comma V, where U is a predecessor. So, all the predecessors which have been scheduled, they are already, we know that they are scheduled, because otherwise we would not have included V in the ready list. Okay. So, these are all the scheduled predecessors already. Now, they have been scheduled at 10, 25 and 18, right. So, what is the time slot at which V can be lower bound at which V can be scheduled? So, just look at this is 10, the delay is 2. So, 10 plus 2 is 12, this is 25 plus 4 is 29 and 18 plus 3 is 21. So, 29 is the large value. So, before the time slot 29 we cannot really schedule V. Why? If we do that, then U 2 would not have completed by that time. So, we take 28 for example, U 2 completes at 29. So, the values computed by U 2 will not be available to V, therefore, 28 is an illegal slot. So, that is what this really is all about. So, the max in this case was this 29, the others did not contribute to the maximum. So, this gives you the lower bound at which the node V can be scheduled, but the precedence constraint on its own will not tell us whether resources available are available for executing V at that lower bound value say of 29. The function satisfy resource constraint checks this availability. So, for example, we start at LB and every time slot LB plus 1, LB plus 2, LB plus 3 etcetera from that point onwards is checked. This says infinity, but you really do not go to infinity because there are only a finite number of instructions, number 1. Each instruction has a finite number of MOS steps and we know that every instruction terminates. So, eventually after a certain number of steps every instruction preceding V would have completed execution. So, resources must become available. So, this will never be really an infinite loop. It is just shown that we do not know how many instructions we need, how many time slots we need to check, that is why this says LB to infinity. So, from LB onwards we check LB, LB plus 1, LB plus 2, LB plus 3 etcetera etcetera, and what we check are exactly the same as what I showed you beforehand. The sum of the resource requirements of various time steps must be less than or equal to R. So, this is the sum of the resource requirements of the other instructions which are concurrently executing with V. Rho V j is the resource requirement of the jth substep of node V. So, these two together tell you about the total resource requirements of the entire sequence. So, this must be true for all values of j from 0 to LV, that is for all substeps of the node V. So, once we find a time slot I at which the resource requirements are also satisfied, and that may be LB, LB plus 1, LB plus 2 etcetera etcetera, we return that value I as the slot at which V can be scheduled. So, for example, take the previous schedule itself. So, here this is sigma V 1, this is V 1, this is V 2 etcetera etcetera, this is V 3 and this is V 4. Why did we show these two in red? So, this is time slot 0, this is time slot 4, this is time slot 9, 10, 11, 14 etcetera etcetera. So, what this particular these two time slots have been left free, nothing has been scheduled, simply because scheduling this instruction V 3 in any one of these violates the resource constraint. So, if we leave this to free, then the resource constraints will not be violated. This is just for the sake of example. It may be one slot, it may be two slots or three slots in practice, but here I have just shown these two as vacant, saying that it is possible that two slots would be left free and then the resource constraints would be satisfied if we schedule V 3 at 11 and V 4 at 14. So, that is why we have left these two slots free. So, the LB would have been 9 because of precedence constraints. So, this is 0, then plus 4, then plus 5, 9. but LB and LB plus 1 are not suitable for scheduling V3 because the resources are not available. Let us say resources are available at 11, that is 11, 12, 13, these 3 time steps resources become available. So, therefore, we can schedule them at that time slot, and then resource constraints will be satisfied, no violations occur. Now, how do we actually order these nodes? So, in the priority ordering here, I said pick the highest priority node in the ready list, right. We did not say what is the priority ordering that we use, that is what we want to see now. Let us consider 2 or 3 of these varieties. One of them is the height of a node in the directed acyclic graph, that is longest path from the node to a terminal node. So, if the longer the path, the higher the priority. Why? If the path is longer, that means there are many instructions which depend on this particular node. So, it is better if that node is scheduled early, that is the heuristic that one uses. So, let me show you an example. So, here is a simple directed acyclic graph. The legend says inside is node number, left side is path length and right side is execution time, below is latency. So, if you look at the nodes here, these are the leaf nodes. For the leaf nodes, we say that execution time of the node is the path length. So, execution time is 1 here. So, path length is also 1, execution time is 2 here. So, path length is 2. When we go to this particular node, so we take the execution time here, path length here, add the delay. So, that becomes 3. We take the path length here, add the delay, that is 0. So, it becomes 2. So, the maximum of these really becomes the path length for this particular node 4, that is what this says, latency n comma m plus path length of m. So, max over all the successors of the node n. So, that we did. So, then for this it is 3 plus 0. So, that is 3 and 3 plus 2, that is 5 here path length, and this becomes 3 plus 1, that is 4. So, this is how path lengths are computed. Let us say when we start scheduling, let us say we consider these 2 nodes, then 4 and 5. So, this has a longer path length, larger path length. So, this node would be scheduled first and not this particular node. Then, so okay, maybe we can even look at the scheduling of this particular DAG before we go to the other heuristic. So, the algorithm says consider the root nodes of the DAG. So, that is 1 and 3, these are the only 2 which will be put into the ready list. So, 1 and 3 are in the ready list, we need to pick the highest priority node from that ready list, that is path length. So, 5 and 4. So, node 3 which has path length 5 is picked because it is higher. So, that is why the schedule indicates node 3 as the first node. Let us assume that there are enough number of resources to execute any number of instructions in parallel. So, we do not have to worry about resource constraints in this simple example. The next example we will look at that also. Then 3 is completed, but then the successor instruction is 4, that cannot be executed until 2 is completed, and 2 cannot be completed unless 1 is completed. So, 1 is one is the only instruction in the ready queue right now. So, we are going to include 1 in in the schedule it in the next time step after 3. There is since the number of resources available is very large, no limitation. So, there is no problem about using resources. So, 1 can be scheduled in the next time slot, because 1 does not depend on 3. So, the next one after 1, the node number 2 can now be included in the ready list. So, because 2 has only 1 as its predecessor, 2 can be now included in the ready list. The minimum time slot at which 2 can be scheduled is this was scheduled, let us say time slot 0 plus 1. So, that is the time slot at which 2 can be scheduled. Okay. So, if so we can compute the time slots at which these instructions can be scheduled in this manner. So, now whereas if we assume that only one instruction can be issued in every cycle, that is you cannot have more than one instruction each cycle, then we have scheduled 3 at time slot 0, 1 at time slot 1, right. So, the minimum available time slot for this node number 2 is sigma of 1 plus 1. So, that is time slot number 2. So, after at the time slot 2 we schedule this node 2 because it has no other predecessors, and once 2 is complete, after time slot number of time slot 0 and at 4 can be scheduled. The reason is node number 3, which was initiated in time slot 0, will complete in 2 time slots. So, by the time we reach time slot 2, 3 would have completed. So, 4 can be scheduled in time slot 3. So, because both its operands are ready, and once 4 is completed, we again have 5 and 6 put into the ready queue. Now, which of these should be picked? Again we use the path length as the criterion, 2 and 1. So, node 6 has path length 2, which is higher than path length 1 of node 5. So, schedule node 6 first and followed by node 5. Now, the ready list is empty and we have assigned a time slot for each one of the nodes in the directed acyclic graph. So, that completes this particular scheduling process for the example. Now, what is the second heuristic that can be used? We can compute what are known as earliest start time and latest start time, E start and L start for each of the nodes. So, what exactly is E start? It tells you that you cannot schedule a particular node earlier than the value of E start. And if you say what is L start tells you that this is the latest time by which you should schedule the node, and if you violate either the E start value or the L start value and schedule it outside these limits, this may result in pipeline stalls. Okay. So, as far as possible we should try to stick to the time slots between E start and L start and schedule the nodes, but E start and L start are really based on precedence constraints. They do not consider any resource constraints. Therefore, we may still have to violate the E start and L start values sometimes because of resource constraints, but then since there are not many resources available, there will be pipeline stalls and that cannot be helped. How do you compute E start V? E start V is computed as the maximum over all the nodes 1 to k. So, you are really looking at the predecessors of the node V, u I comma V. So, u I are all the predecessors, there are k of them. So, you consider the E start value of u I and the delay of the edge u I comma V, take the max over it, that gives you E start of V. So, let us see how this is done. So, you have node V here, which is to be for which you want to compute E start. These are the 3 predecessors. So, u 1, u 2, u 3. So, they have their E start values already computed. Okay. So, that is 25, 45 and 16, let us say. The delays are d 1, d 2, d 3, 4, 7 and 2 respectively. So, you look at 25 plus 4, at 45 plus 7 and 16 plus 2. So, that means 29, 52, 18, the max is obviously 52. So, this is how you compute the E start value. So, this tells you that we cannot start before time slot 52. Okay. So, that makes sense because we are really looking at the minimum time at which all the 3 predecessors of the node V complete, that is 45 plus 7. Okay. Now, the E start value of the source node is taken as 0. We begin the computation of the E start value from the top, assuming the source node has a 0 E start value. What about L start? It is from the bottom. So, L start u is computed as minimum over all the successors. So, you want to compute the L start value of u, there are successors for you, those are all the V I nodes 1 to k. Take the L start of the successor node, subtract the latency and take the minimum of this particular computation over all the successors. So, let us see what we mean. There are 3 successors, again we want to compute the L start value for V, W1, W2, W3. Their L start values are 12, 36 and 21. So, now what is the L start value for node V? 12 minus 2, 36 minus 1 and 21 minus 3. So, the minimum of all this is 10. So, that is the latest time at which node V can be scheduled. So, if you schedule later than that, then you know we are going to create some pipeline stalls, that is very obvious, you see. So, if this is let us say 10, so 10 plus 2 is 12 here and 10 plus 1 is 36 and 10 plus 3 is 13, right. So, if you this can be scheduled at time slot 2, that is why 10 plus 2 is 12. So, if you actually exceed L, then this node will not be scheduled at 12, it will be scheduled at some other value. So, there would be some kind of a stall, but that cannot be helped if there are not many resources available. So, now once we compute the E start value starting from the top, the L start value of the sync node is set as its E start value and we start computing the L start values from the bottom towards the top. So, E start and L start can be computed using a top down and bottom up pass respectively, either statically before scheduling begins or dynamically during the scheduling itself. Okay. So, you know if you actually want to schedule the precedences rather the E start and L start values during the scheduling process, because the graph is going to change as and when we schedule certain nodes, it can be done, but that requires a little extra computation at schedule time. So, a node with a lower E start or L start value has a higher priority, that is one possible heuristic, but a slightly better heuristic would be consider slack, which is L start minus E start. You are really looking at an interval E start L start minus E start during which you want to compute, we want to schedule a node. So, it makes sense to consider nodes with a lower slack and give them higher priority. That is because E start and L start are very close. So, there is not much gap between them. So, those nodes get higher priority, and those which have higher slack value, they can be they have many more slots in which they can be scheduled. So, they get a slightly lower priority. Instructions on the critical path may have a slack value of 0, their L start and L start values actually may coincide and hence they get the maximum priority. So, this is an example which we saw already. So, here is another example. So, let me show you how the E start values and L start values are really computed. So, for example, if you look at this particular graph, the add, sub and store values are supposed to have 1 cycle, 2 cycles and 3 cycles respectively. In either add, sub, store has 1 cycle latency, load has 2 cycles latency and mult has 3 cycle latency. The path length and slack are shown on the left side and right side of the parentheses. Okay. So, 8 is the path length and 0 is the slack, okay. Whereas, within the parentheses we are showing E start and L start. So, we start with a value of 0 for E start and then we compute 0 plus 2 as the E start value for add, 0 plus 2 for the E start value of sub, and from here 2 plus this add 1 3. is one possibility for this particular add node, whereas on this side 2 plus 1 is 3 is the only possibility for the node mult. And then we have for this particular node we have 3 delay slots for multiply. So, 3 plus 3 6 is the E start value for add. So, this side we get 3 and this side we get 6. So, E start really is the max of these. So, it is computed as 6 and then plus 1 is 7 for this particular node S t. So, this is how E start values are computed. So, we will stop at this point, continue this example in the next lecture, where we are going to discuss in more detail how the L start values are also computed and used for scheduling. Thank you.